CUDA out of memory. Same model, same GPU, same red text in your terminal, and four completely different things could have caused it. The usual advice is to lower the batch size, which sometimes works and almost never tells you why. Because that one error message is really four different tenants, all fighting for the same space. Here's the thing about that error, it reports space, not cause. It tells you the GPU filled up. It doesn't tell you what filled it. So we're going to treat this like an investigation, with four suspects on the board, and work through them one at a time. One model threw out, Qwen 2.57b, 7.61 billion parameters. The four things competing for memory are the weights themselves, the KV cache holding conversation history, the activations kept alive for the backward pass, and the training state, gradients, optimizer, master weights. What makes these four genuinely different suspects is that they don't grow for the same reason. Weights track model size and precision. KV cache grows with tokens and active conversations. Activations follow the shape of your workload, and full training state scales with how many parameters are actually trainable. We're not chasing the last megabyte here, we want to know which tenant is driving the crash. That distinction matters, because trial and error tweaking might land you on a config that runs, but it never explains why the previous one failed. Total VRAM is a running sum, weights, plus KV cache, plus activations, plus gradients, plus optimizer and master state, plus runtime workspace. Keep this strip in mind, because every case we look at is really just one of these terms swelling up. Some of these we can calculate exactly. Weights, KV cache, gradients and optimizer state all follow from parameter count, architecture and precision. Activations and workspace are illustrative estimates, since they depend on kernels, checkpointing, and the framework. And FP16 or BF16, it's 2 bytes per parameter either way. The first two cases are inference, which means no backward pass, so gradients and optimizer states simply don't exist yet. That leaves weights, KV cache, and a bit of runtime workspace as the only things in the room. Case 1 is as simple as it gets, a single T4 with 16 gigabytes, one request, a short 2000 token context, inference only, FP16. Barely any workload at all. And the model hasn't even started answering yet. 16-bit weights mean 2 bytes per parameter, since 8 bits make a byte. So 7.61 billion parameters, at 2 bytes each, comes out to about 15.22 gigabytes of weights alone. That's the model storage floor on a 16 gigabyte card, before a single token of cache, workspace, or runtime gets added on top. Stack it up. The weights take 15.22 gigabytes. The KV cache for that short context is a rounding error, about 1/10 of a gig. Forward workspace, maybe half a gig, and a runtime allowance of around 2. That lands near 17.8 gigabytes on a card that holds 16. Out of memory. Short conversation. No optimizer. Nothing exotic happening at all, the baseline model just left no usable headroom before the workload even started. First culprit, weights. 1 card flips over on the suspect board, and 3 are still open. If the weights are what failed, then the weights are what you change. 4 bits is half a byte per parameter, so those same 7.61 billion parameters come down to about 3.8 gigabytes. Same architecture, same prompt, same GPU, the only thing that changed is how the weights are stored. In practice you won't see 3.8, you'll see closer to 5 gigabytes loaded, because a quantized model also carries scale factors and metadata, some tensors stay at higher precision, and storage layout adds alignment overhead. The raw arithmetic is the floor, 5 gigabytes is what actually sits in VRAM. Rebuild the same stack with a 5 gigabyte model and everything else unchanged, and you land around 7.6 gigabytes on a 16 gigabyte card, with real headroom to spare. Quantization fixed the tenant that actually failed, which is exactly why it isn't a universal fix. When weight storage is the dominant tenant, the useful levers all attack the weights directly rather than the batch size. You can quantize, which is what we did here. You can pick a smaller model, though that's a capability trade-off. Or, if precision has to stay high, you shard across GPUs and pay in hardware and communication, or offload part of the model to CPU and pay in speed. For case 2 we reset 2 things deliberately, a bigger GPU, an A100 with 40 gigabytes, and weights back at standard 16-bit precision. That way whatever fills this card next is genuinely a new tenant, not leftover quantization doing the work. Still inference, precision fixed, context fixed at 32,000 tokens. The only thing we vary is how many conversations are active at once. Every one of those conversations stores its past keys and values so they don't have to be recomputed each time a new token arrives, and that history has to live somewhere. Per token, per request, the cache holds two tensors, a key and a value, across 28 layers, with 4 KV heads, 128 values each, at 2 bytes apiece. That 4 is worth pausing on. Quinn uses grouped query attention, so 28 query heads share only 4 KV heads. Multiply it out and you get about 56 kilobytes per token. Now stretch that across a full 32,000 token conversation. 56 kilobytes per token, times 32,768 positions, works out to roughly 1.88 gigabytes for one request at full context. Hold on to that block, it's the unit we'll be stacking. And these caches don't pool together. 11 active conversations don't share one cache, they keep 11 separate histories alive, each with its own 1.88 gigabytes. Concurrency multiplies, because the cache is request-specific by design. You can predict where this breaks before you ever launch. Start from 40 gigabytes of capacity, subtract 15.22 for the weights and another 2.5 for workspace and runtime, and you're left with about 22.3 gigabytes of room for cache. Divide that by 1.88 per request, and the boundary sits at just under 12. So 11 users fit weights, cache and workspace come to about 38.4 gigabytes, tight but under the line. Add a 12th and you're at 40.3, past the limit. Nothing leaked. Nothing doubled. One steadily growing tenant crossed the line. For CUDA cache pressure, the levers work on tokens and active requests, not on the weights. Shorten the context, or cap concurrency, since each extra 32K request costs another 1.88 gigabytes. You can also quantize the cache or offload it to CPU, trading memory against latency or transfer cost. Paged allocation helps with fragmentation, but it doesn't change what a token actually needs. That finishes the inference half. Switching to training changes the equation itself. A backward pass now exists, which means activations have to survive long enough to compute gradients, and depending on the method, gradients and optimizer state show up too. Two suspects still open. Case 3 is QLoRA on a T4. The base model stays frozen and quantized to 4 bits, and only the small adapter parameters are trainable. Gradient checkpointing is off. Deliberately, we want to see exactly what batch size and sequence length do to saved activations, with nothing hiding the effect. Two knobs matter here. Batch size is how many examples run together, and sequence length is how many token positions are in each one. Both of them multiply how many intermediate values have to stay alive, waiting for the backward pass to come collect them. The teaching estimate goes like this: batch time sequence, times the hidden width of 3584, times 28 layers, times roughly 10 saved intermediate tensors, times 2 bytes. That 10 is not a Quinn constant, it's an illustrative multiplier, because real saved activation memory depends on which tensors backward actually needs, the attention kernel, the type, the framework. Normally you'd turn on gradient checkpointing, which saves fewer intermediates and recomputes the rest during backward. It's a good trade. But it would smooth out exactly the effect we're trying to show, so for this case it stays off. Before we touch either knob, some of the bill is already locked in: the quantized base model, the adapter weights, their gradients and atom state, plus a runtime allowance. Together that's about 8 gigabytes that doesn't move no matter what we do to batch or sequence. Baseline is batch 1, sequence 512, about a gigabyte of activations on top of the fixed 8. Quadruple the batch, you're at 12. Quadruple the sequence instead, also 12. But do both, and the multipliers compound into 16 times, activations jump to 16.4, and the total hits 24.5 on a 16 gigabyte card. The weights never grew. The workload did. When activations are the problem, you make the workload remember less at once. Drop the micro batch size and use gradient accumulation to keep the same effective batch, or cut the sequence length, often the strongest lever for long context training. Then there's gradient checkpointing, trading compute for memory, and fused attention kernels. The usual order: lower whichever knob spiked first, then reach for recomputation when you need that batch or context back. For the last case we remove batch and sequence as suspects entirely, batch back to 1, sequence back to 512, and we even upgrade to an 80 GB A100. Then we switch from QLoRA to full parameter training, where every weight in the model is trainable. Both Case 3 and Case 4 are training runs, but they fail for opposite reasons. Case 3 was dominated by workload-dependent activations. Case 4 is dominated by fixed training state, because all 7.61 billion parameters are now trainable and every one of them carries its own gradient and optimizer bookkeeping. In a standard mixed precision layout, each parameter carries 2 bytes for the forward weight, 4 for an FP32 master copy, 4 for its gradient, and 8 more for Adam's 2-moment estimates, 18 bytes per parameter, total. That's a reference accounting model, not a law. Different optimizers, types, sharding and offload all change the real bill. 7.61 billion parameters, at 18 bytes each, comes out to roughly 137 gigabytes of fixed training state. On an 80 gigabyte A100, the optimizer moments alone are more than 60 gigabytes bigger than the whole GPU. And no activations have been added yet. Batch of 1. Sequence of 512. It changes nothing, because those knobs only control workload-dependent memory, and this bill was already fixed at 137 gigabytes before the first forward pass. Fourth culprit, full training state. The board is complete. This is exactly why PEFT exists. Full fine-tuning creates gradients and optimizer state for billions of parameters, so if your task doesn't need every base weight updated, you freeze the base and train small low-rank adapters instead, and the expensive tenants now scale with adapters, not with all 7.61 billion. QLoRA goes one further by keeping that frozen base quantized too, attacking both tenants at once. When full fine-tuning genuinely is required, you distribute the bill, FSDP or Zero-style sharding splits parameters, gradients and optimizer state across GPUs, or you offload some of that state to CPU and pay in throughput. One caveat worth remembering, PEFT solves trainable state memory, but it doesn't touch activations. Case 3 proved that. For suspects, 4 verdicts. Weights grow with precision, so you quantize. KV cache grows with context and concurrency, so you shorten or throttle. Activations grow with batch and sequence, so you shrink the workload or recompute. Training state grows with trainable parameters, so you use adapters or shard. There's no universal fix, because the pressure came from 4 different places. The most useful debugging question is simply what changed right before the crash. If only precision changed, look at the weights. If context or active requests grew, look at the cache. If batch or sequence grew during training, look at activations. And if you switched from adapters to full training, it's the fixed training state. We know where the memory went, every gigabyte of it accounted for. Next we open up the GPU itself and ask why this particular machine is so good at the math that language models need, and why its memory is so precious in the first place. So, out of memory is a symptom, not a diagnosis. Figure out which tenant is dominant, then pull the tenant's lever, because the fix that saved case 1 would have done nothing for case 4. If this is the kind of thing you want to actually understand rather than guess at, subscribe and stick around for the rest of the series.